Okay guys, so let's look at the matching. Hear how we came up with these. So what do we put for letter A? C is correct. And what about letter B? Good. Hold on, page though. And what about letter C? And D? E? And F. Good. So some things we looked for was that in behavior. For example, on this one, we know it's a quadratic. We also know that because it's a quadratic, it's a parabola. We knew that it had to have a y-intercept of 0, -4. So we're looking for the parabola with a y-intercept of -4. It had to be letter C. Okay, so we can do those pretty quickly. All right, let's go over to page 113. We're going to define a local maximum. A local maximum, if you look back at page 111, I'm just going to show you an example of some local maximums. Right here, this would be a max. Right here, this would be a max. And these are called local. The reason they're called local is because of the region that they're in. Compared to the points right around them, it's a high point. Okay? So for these first 4 right here, this is a local max, that's a local max, and that's a local max. So what we can define a local max as being is, this is going to be the y value of a turning point. Turning just means changing direction. A turning point higher than all nearby points. So the y value of a turning point higher than all nearby points. So looking back here, so right here I would call this local max, that's going to be 1. This local max is going to be -1. This local max is going to be 2, because all I'm telling you is the y value at that point. That's how we define the local max right there. So for the local min, this is, of course, is going to be the y value of a turning point. This means changing directions lower than all nearby points. Y value of a turning point lower than all nearby points. So looking back again, right here, see how this would be a turning point. We're going from decreasing to increasing. So right here, this is going to be a local min of -2. Okay? Got that? So that's something we're going to be looking at, are for these local maximums and local mins. So come down here. These are 2 important concepts, actually 4 altogether, but the first 2 I want to look at are zeros and solutions. These are going to mean the same thing, okay? In order to find a zero, that's going to be what makes the function equal 0. A solution is what makes the function equal 0. So they're basically the same thing. It's just that this is starting with polynomial function notation, whereas this one will already say, like, the whole entire function equals 0. Okay? A factor is going to be a factor of the polynomial. X minus k will be a factor, and this is going to be true if k during synthetic division results in a 0 remainder. So you've done this all the time. We want to know, is x minus 2 a factor? We put 2 into the box using synthetic division. If we get a 0 for the remainder, yes. X-intercept. If k is a real number is important, then k is going to be an x-intercept. as long as it passes through K0. What this means is, if we have a 0 and it's real, then it's going to be an x-intercept. Real zeros are x-intercepts. Imaginary zeros are not. So real zeros are always going to give us x-intercepts, where imaginary zeros are not going to be x-intercepts. Let's look at an example of what we're trying to do. Our goal is to be able to graph functions. So here's our function. F of x equals 1/2 x plus 1 times x minus 4 squared. The first thing I'm going to do is find zeros by setting this function equal to 0. I'd multiply both sides by 2 to get rid of the 1/2. What is it that's going to make this equal 0 then? What are my real zeros going to be? What is it, guys? Solve it. It's pretty easy. It's already factored for us. So what makes this equal 0? -1. And what makes this equal 0? 4. Those are my two real zeros. However, because this is used twice, this is actually going to be a real 0 twice. And what's that going to result in as far as the graph goes? It's going to result in a bounce. The next thing I want to look at is the degree. This is x to the first, this is x to the second. So the degree of this is going to be 0. It's going to be 3. So if the degree is 3, we need to think of the end behavior. This is a positive out in front. We have to have opposite end behaviors. That's going to be our end behavior of the function. So now, like I said, we're going to graph this. So we've got -1 is a real 0. 4 is a real 0. I want to find some other points, though, to make this good, to make this a strong, accurate graph. So I might want to check some other points, like 0 and 2. To find these y values, I have to plug them back into my function. So 0 plus 1 is 1, 0 minus 4 is -4, -4 squared is going to be 16 times 1 is 16, half of 16 is 8. 2 minus 4 is -2, squared is 4, times 3 is 12, half of 12 is 6. I'm just finding some values. So at 0, 2, 4, 6, 8, I'm at 8. At 2, I'm at 2, 4, 6. Now, I have to see if this is enough information. I really don't have to check any numbers down here because I know this is a 0. Can the function come back up again if that's my only -0? No, it's got to continue down like this. So it's going to come up, it's going to come down. Now, is it going to pass through this or is it going to bounce off of that? It's going to bounce, isn't it? So it's going to come down, it's going to bounce, and it's going to go back up. And that's going to be a pretty good graph to represent that function. Okay? That's one thing you're going to do. Come over here for a minute. The location principle. This sounds kind of complicated if you read it. It says if f is a polynomial function and a and b are two real numbers such that f of a is less than 0 and f of b is greater than 0, then f has at least one real 0 between a and b. Guys, this is all it's saying. It's saying if you have a y that's negative and then you have a y that's positive, then there has to be a real 0 in between there. Look at this graph right here, this table of values, rather, for the graph that I have. Do you notice how this y is -3 and this y is 6? Think about if I were plotting these points. -2, -3 would be right here. Then my next point is -1, 6, right about there. What is going to happen in between those 2 points when I connect them? What are we going to have to pass through? 0, right? I'm going to have to hit the x-axis to graph these points. Look, we got this, then it has to come up like that. Do you see how we crossed the x-axis right there? So in between here and here, we have to pass through 0. So in between -2 and -1, there would have to be a solution there. There would have to be an x-intercept. There would have to be a 0. All of those things mean the same thing. So if our graph looks like this, and this point down here is -3, -2, -3, and this point here is -1, 6, then it has to pass through 0 in between x equals -2 and x equals -1. There must be a 0, also called an x-intercept, also called a solution. That makes sense to you guys. That's all that principle is saying. All right, so now let's do an actual problem here. Find all zeros, all real zeros, of this. Of f of x equals 6x to the third plus 5x squared minus 17x minus 6. Do you remember how we can find that first 0? How can we find that first one? This is just like what you did last night for homework. What do? Look at it on the calculator, right? So if I looked at this on the calculator, we're going to pretend we already looked at it, we find that x equals -2 is one of our zeros. Now what do we use, guys? Synthetic division. -2 into 6, 5, -17, -6, 5. So then we have -12, this is -7, this is 14, this is -3, this is 6. If this was to the third, then what is this to? Second, right? So we have 6x to the second minus 7x minus 3 equals 0. I have one of my real zeros. I have to find the other two real zeros. So I would now have to try to factor this. I'm going to have 3x and 2x. I know it has to be 3 and 1, but I'm not going to put a 3 there. Never have the same number in that parentheses. Do you know how the signs are going to have to go? To get a -7x, that's a 9x, that's a 2x. How do the signs have to go, guys? There you go. And so now we can find our other two zeros. One of our zeros is x equals -2. Solve this now. Can you solve it quickly? 3x plus 1 has to be 0. What's it going to be? -1/3. Good. And then where's the other 0 going to be? 3/2. And if I looked at a table of values, I would be able to tell that. I'd be able to see that in between 0 and -1, here's the solution. In between 1 and 2, here's the solution. Okay? Homework will be pretty easy. It's just like this and the graphing. The other stuff we'll talk more about tomorrow. Good job. Have a good night. Homework's on the assignment sheet.